2.7% does not sound like much until you understand what it measures. It measures the probability that a 340-meter rock strikes Earth on a specific date. April 13th, 2029. That number held for 3 weeks and refused to fall. Every previous asteroid threat in the history of tracking had dissolved within days. Better data arrives, uncertainty collapses, the rock slides safely into the margin. That is the normal arc. That is what always happens. Except once, it did not. The rock was 99,942 Apophis, named for the Egyptian serpent that swallows the sun. Scientists do not name hazards dramatically as a rule. This one, they felt, had earned it. To feel what 2.7% actually means, stand in front of a roulette wheel. Find a number, any number, bet everything on it. Spin the wheel. Your odds of winning are 2.7%. You are playing that game with a city. Maybe your city. Maybe a coastline. Maybe an ocean that feeds 3 continents. The people inside JPL who first saw the number did not panic. They went quiet. Quiet is what happens when experienced scientists encounter something genuinely new. Paul Chodas had spent his career watching probabilities flicker and die inside a week. He had never seen one sit this high this long. He went back to the data a 3rd time. The data said the same thing. Roy Tucker and David Tholen found it on June 19, 2004. 2 astronomers at Kitt Peak processing survey images before sunrise on a routine night. They cataloged it as 2004 MN4, one dot among thousands moving against fixed stars. The initial orbit looked unremarkable. Orbital mechanics disagreed by December. Before the year ended, every major observatory with access to the southern sky was watching. None of them made the number fall. Pre-covery images from Australia in late December helped. Older photographs of the same sky, taken before anyone knew what to look for in them. More data should reduce uncertainty. In this case, it briefly raised the probability higher. 2.7%. Highest score ever recorded on the Torino Impact Hazard Scale by a wide margin. The scale was designed by MIT professor Richard Benzel in 1999. It runs from 0 to 10. 0 means the rock is irrelevant. 10 means prepare every government on Earth immediately. Apophis scored a 4. In 5 years of the scale's existence, nothing had touched above 1. A score of 4 means meriting attention from astronomers and government officials worldwide. The language of the Torino scale is careful. The implication is not. The world had been told about asteroid risk before, abstractly, statistically, in percentage terms. Scientists had given talks about Chicxulub and mass extinctions and orbital resonances. They had published papers with probabilities expressed in terms of once per 100 million years. The public had listened politely and filed it under the same category as supervolcano risk. Something real in theory, geological in timescale, something someone else would worry about. Apophis was different in the specific way that made it impossible to file away politely. It was not a statistical distribution across a million years. It was a date. One date. April 13th, 2029. You could count the years on your fingers. Children alive in 2004 would see it. This was not an abstraction. This was an item on a calendar that already existed somewhere. The Bruce Willis movies had not prepared anyone for this, it turned out. Fiction imagined the asteroid as sudden, cinematic, discovered weeks before impact. The reality of Apophis was slower, quieter, and in some ways more destabilizing than that. A number on a screen that would not go away. A date that sat there for 3 weeks. The anxiety it generated was the specific kind that knowledge creates when action is unclear. You know, the thing. You cannot yet do anything about the thing. You wait and watch the number. 1,200 megatons of energy released on contact with the surface of the Earth. Hiroshima was 0.015 megatons. Run the division yourself and sit with the result for a moment. The newspaper editors ran it for their readers across 40 countries in 48 hours. Asteroid could hit Earth in 2029, 30 languages, front pages, the number everywhere. What followed in the scientific community was not panic and not denial. It was Arecibo. The 305-meter radio dish in Puerto Rico was the largest single-aperture telescope ever built. Carved into a natural sinkhole in the jungle hills north of the city, operational since 1963. Its original purpose was the ionosphere. Its real career was the solar system and beyond. Radar astronomy works on a principle almost childlike in its simplicity. You shout, you listen. Transmit a pulse toward a target. Measure how long before the echo returns. Calculate distance. Measure the Doppler shift in the returning signal. Calculate velocity. Pin the orbit. No photographic plate, no CCD camera, no optical telescope can match what radar accomplishes here. Radar does not measure where the light of an object appears. It measures where the object is. Dr. Stephen Ostro at JPL coordinated 3 nights on the Arecibo dish in January 2005. The target was 250 million kilometers away. The signal degraded with the square of that distance. What came back was faint. The dish at 305 meters collected what nothing smaller could touch. Ostro's team fed the measurements into the orbital model at JPL. The uncertainty region collapsed. The corridor of possible positions, previously spanning a frightening range, shrank to a sliver. April 13, 2029, Apophis would pass Earth. Not hit it, pass it, closely, but pass. JPL released the result on January 14, 2005. The impact probability for 2029? Effectively 0. 3 weeks of a number that refused to fall. 3 nights of radar, and it was gone. The press coverage of the resolution was a fraction of the coverage of the alarm. This asymmetry is not unique to Apophis. It is how threat and resolution always travel. Fear moves fast. Correction moves slowly. This matters for how the public understands risk. But inside the scientific community, the resolution of 2029 immediately opened a different door. Buried in the refined orbital solution was something that required a new kind of attention. A gravitational keyhole. A region of space approximately 600 meters wide in the orbital path. The concept requires a moment to sit with because it is genuinely strange even to specialists. During a close planetary flyby, Earth's gravity can act on a passing asteroid in a precise way. Not pulling it into a collision, something more indirect and in some ways more unsettling. Bending the trajectory at a specific angle so that the next return pass hits differently. Earth reaches forward through time, using one flyby to set up conditions for the next one. If Apophis threaded that 600-meter keyhole during the 2029 pass, April 2036 became the problem. The probability was 1 in 45,000. Small, not zero. On this particular rock, not zero mattered. The history of 2.7% had made the planetary science community unwilling to dismiss small. Beyond 2036, the orbital mechanics produced further resonance windows, 2068, 2085, beyond. Each one dependent on whether 2029 threaded the keyhole correctly to set up the next alignment. So, Apophis did not leave the watch lists in January 2005. It changed which list it sat on. From imminent threat to long-term surveillance required. The difference in urgency was real. Kinetic deflection is the straightforward answer when the object is found early enough. Hit it with a spacecraft. Transfer momentum. Alter velocity by a fraction of a meter per second. Over years, that fraction accumulates into a trajectory shift measured in thousands of kilometers. Thousands of kilometers is the difference between a keyhole and empty space. NASA demonstrated this on September 26, 2022, with the DART mission at the asteroid Dimorphos. DART was a spacecraft roughly the mass of a vending machine. Dimorphos was 160 meters across. DART struck at 22,530 kilometers per hour, observed in real time by a small trailing CubeSat. The orbital period of Dimorphos around its parent asteroid Didymos changed by 33 minutes. The mission target had been 73 seconds. The actual result was 27 times more effective than required. The ejecta plume acted as an additional thruster, pushing far beyond the impact force alone. Kinetic deflection works. It works better than the conservative models predicted. It works at scale. The test removed every qualifier from the deflection discussion. Deflection moved from concept to demonstrated, measured, repeatable fact. The lesson DART taught is that we do not need exotic technology to move an asteroid. We need time. Lead time translates directly into deflection effectiveness. Find it with 25 years of warning, and a single DART-scale mission resolves the problem completely. Find it with 5 years, and you need dozens of missions in rapid succession under enormous pressure. Find it with months in physics limits what any civilization on Earth can accomplish in time. Apophis gave 25 years. The system used them. That combination is not guaranteed to repeat. There is a version of this story that ends very differently. In that version, Tucker and Tholen's survey images are never processed before December 2004 ends. The rock gets cataloged and sits in a backlog. Orbital mechanics stays uncertain through 2028. With 1 year of warning, the deflection math changes entirely, and not in our favor. A DART-scale mission launched in 2028 cannot alter an Apophis-sized trajectory by enough. The numbers work differently when the lead time compresses from decades into months. Physics does not negotiate. The rocket equation does not make exceptions for late arrivals. In that version, April 13, 2029 ends the way the mythology of Apophis always promised it would. We do not live in that version. We live in this one. The difference is the survey. The specific survey running at Kitt Peak in June 2004. The specific telescope. The specific night. Two people doing unglamorous work before sunrise who happened to find the right moving dot. This is the part of planetary defense that requires the most imagination to appreciate fully. The heroism in this story belongs to people whose names most of the world has never encountered. Not to astronauts. Not to mission controllers in dramatic rooms with countdown clocks above them. To survey astronomers working overnight in cold domes, processing thousands of objects per session. To orbital mechanics staff who run the same calculation 4 times because the number looks wrong. To radar engineers calibrating a Puerto Rican dish to ping rocks drifting through the asteroid belt. To the people who wrote the 1997 and 1998 budget justifications that funded the Space Guard survey. None of these people stood in front of a camera when the March 25, 2021 announcement was made. The announcement came from scientists, but the infrastructure making it possible involved many more. Planetary defense is collective work. From outside, it appears as isolated individual discoveries. Each discovery is real. The infrastructure that made each discovery possible is the actual story. Arecibo existed because engineers in 1960 decided that sinkhole was worth carving into a telescope. Goldstone existed because deep space communication required a large dish in the California desert. Neither was built for Apophis. Both were available when Apophis needed them. This is how civilizational infrastructure works when it functions. It waits before the need arrives. The fire station does not build itself the week a house catches fire. It exists in anticipation. Planetary defense is the fire station for the largest category of preventable catastrophe on Earth. The category that ended the Cretaceous. The category we are, for the first time, able to prevent. Not eliminating the risk entirely. Preventing the specific event that finds us with enough warning. Apophis found us with 25 years of warning. The infrastructure existed. The outcome followed from it. The next rock might give us 8 years. The infrastructure needs to be ready by then. It is improving. The gap between getting better and sufficient is measured in funded telescope time and missions. It is measured in budget lines nobody reads and survey programs that generate no dramatic headlines. It is measured in the patience of a civilization solving problems before they announce themselves. NASA assigned permanent staff to the problem. ESA's Coordination Center in Frascati did the same. For 8 years, the measurements accumulated. Each observation slightly tightened the orbital model. 2013, new data eliminated the 2036 window. The orbital solution had become precise enough to know. Apophis would miss the keyhole in 2029. The 2036 probability fell to 0, just as 2029 had. 2068 remained open. Small probability, but the community had learned its lesson about small. Inside the calculations, something had been quietly waiting for better data to resolve it. The Yarkowski effect. Named for a Polish engineer who described it in a pamphlet around 1900. Ivan Yarkowski's core insight, heat, is not neutral. Heat has direction. Direction has consequence. Every asteroid absorbing sunlight and re-emitting it as thermal radiation experiences a tiny push. The push is invisible. It is unmeasurable directly. Over decades, it accumulates into orbital drift. Move an asteroid by a few hundred meters per year for 20 years, and the trajectory changes. Change the trajectory by a few kilometers, and a 600-meter keyhole becomes a question of precision. The Yarkovsky drift rate depends on composition, rotation, surface texture, reflectivity. None of these were known for Apophis with enough precision to calculate the 2068 drift reliably. Without it, the 2068 prediction carried uncertainty too large to formally close the window. Then came December 2020. Without warning, Arecibo collapsed entirely. The support cables holding the 900-ton instrument platform above the dish snapped without warning. The platform fell. The dish was obliterated. The most powerful planetary radar on Earth was gone. It had been there when Apophis was discovered. It had been the instrument that resolved 2029. Now it was rubble in a Puerto Rican jungle 6 years before the flyby it was meant to study. The community reorganized around what remained. Goldstone's solar system radar in California was next. The 70-meter dish in the Mojave Desert, operated by NASA's Deep Space Network, less sensitive. Less sensitive is not the same as useless. The 2021 apparition would bring Apophis close enough. And there was something Arecibo had never had: 17 years of accumulated positional data to work with. An astrometric baseline long enough that the Yarkovsky drift could be isolated from everything else. Dr. David Farnokia at JPL built the analysis from the complete observational record since 2004. Goldstone ran its observations in March 2021. The measurements came in across multiple nights. The drift rate for Apophis, 170 meters per year, directed away from every threatening keyhole. Not toward resonance corridors, away from them. The orbital model updated in real time. 2068 fell below 1 in 100,000, then 1 in 500,000, then past what the software expressed normally. On March 25, 2021, NASA announced it. No impact trajectory through the end of this century. ESA removed Apophis from its risk list the following morning. Sentry delisted it the same week. 17 years between the number appearing and the number being permanently retired. What changed after Apophis goes beyond the specific threat being resolved in 2021. The 17 years between 2004 and 2021 changed how planetary defense thought about itself. Before Apophis, planetary defense was largely theoretical within the broader scientific world. Important, yes. Funded somewhat, but not treated as urgent infrastructure the way it needed to be. Apophis arriving at 2.7% forced a different kind of institutional seriousness onto the field. Congress held hearings. Agencies received budget requests framed around the Apophis case directly. Coordination that had been informal became formal overnight. Data sharing agreements were codified. The question shifted from, should we have this infrastructure, to, how do we improve what we have? That shift in framing produced different kinds of conversations in different kinds of rooms. DART would not have been approved as quickly without Apophis having demonstrated the stakes first. The Vera Rubin Observatory's survey component did not happen in a vacuum separate from this history. Space-based infrared survey proposals gained traction they would not have had before this near miss. Apophis was not the first threat ever tracked. It was the first to force real institutional change. The infrastructure that finds the next Apophis, still unnamed in the survey backlog, is better now. Not perfect, not complete, but measurably, demonstrably better than it was in December 2004. That is what a 2.7% number does when it stays on the screen for 3 weeks. It does not just test the current system, it builds the next one. What the story of 2.7% actually teaches is not about asteroids specifically. It is about the difference between what science can do with time and what it can do without it. 3 weeks was enough to alarm the world. 3 nights of radar was enough to resolve 2029. 8 more years was enough to close 2036. 17 years total was enough to close everything. The system that produced this outcome was not assembled in response to Apophis. It preceded it. Congress mandated the Space Guard Survey in 1998. Telescopes began cataloging near-Earth objects. Arecibo had done planetary radar astronomy for decades before Tucker and Tholen found their dot. JPL's Center for Near-Earth Object Studies was staffed before December 2004 produced its number. The infrastructure was in place. When the specific threat materialized, the infrastructure worked. That is the part of the story that gets lost in the drama of 2.7% and the relief of 0. Not the discovery, not the resolution. The years of unglamorous, funded operational work in between. Work producing no headlines because it mostly confirms what is already known. The sky is safe today. The sky is only safe today because someone checked it yesterday and will check it tomorrow. As of 2024, less than half the estimated population of 140-meter-plus objects is cataloged. Objects the size of Apophis are still appearing in survey data on a regular basis, still unnamed. The Vera Rubin Observatory in Chile will transform this when it reaches full operational capacity. A space-based infrared survey could find dark asteroids invisible to every ground-based telescope. These are not hypothetical. They are instruments partially built or currently in active development. What they are not is fully funded and prioritized in the way the Apophis story argues they deserve. The most dangerous object in the solar system right now is not the one being tracked most carefully. It is the one that has not appeared in a survey image yet, the one with no name and no probability. Apophis is safe. Apophis has been safe since January 14, 2005 in practical terms. April 13, 2029 is still coming. It is worth understanding what that night will actually look like. 31,600 kilometers, the closest calculated approach distance, closer than geostationary orbit itself. The ring of communication satellites carrying GPS and broadcasts sits at 35,786 kilometers. Apophis will pass below that ring, below the infrastructure that modern civilization runs on. Not threatening it, not interacting with it, simply crossing through its altitude band in the dark. Observers across Europe, Africa, and Western Asia will see a magnitude 3.1 point of light moving. Not drifting across weeks like a planet, visibly fast, crossing the observable sky in minutes. A 340-meter rock showing its velocity to anyone who simply looks up at the right time on that night. Roughly 2 billion people will be positioned to see this without any equipment at all. No other large asteroid is calculated to come this close in any window current models can see. The 2029 flyby will be studied before it happens. Telescopes are already being reserved for it. Every major observatory capable of observing at the relevant declination has the date blocked. Radio facilities plan to track it across the approach, closest approach, and recession. Amateur astronomers across Europe and Africa are already aware it is coming. The event has a quality that solar eclipses have, known in advance, unrepeatable in your lifetime. When the rock crosses below the satellite ring, something changes about how the solar system feels. It stops being a thing taught in school and becomes a thing visible from your own backyard. A generation that watches Apophis pass will carry a different relationship to planetary science. Not as abstract cosmic processes, but as observable physics happening directly overhead in real time. The asteroid belt is not some distant concept. It sends visitors. We have already met one. Schools across Europe will likely hold observing events. Planetariums will stream it live. Magnitude 3.1 means it will be clearly visible in suburban skies without any dark adaptation needed. Brighter than most of the stars in the familiar spring constellations visible that same April night. The experience will be unlike any previous public astronomical event in one specific way. It will be fast, not imperceptibly slow like a planet, not brief like a meteor. Something in between, a speed that registers as motion to the naked eye in real time. The solar system making itself visible at a human scale for the first time in this generation. Earth's gravity will act on Apophis during those hours. Tidal forces measurable in geological terms. Material undisturbed for 4.5 billion years on its surface will shift and settle under the pull. Slopes resting at their natural angle since the early solar system will readjust under tidal stress. The Apophis of 2029 will not be identical to the rock that departs. Earth will have touched it, without any collision, purely through the invisible reach of planetary gravity across empty space. A spacecraft will be there, positioned and waiting to watch everything. OSIRIS-REx returned samples from the asteroid Bennu to Utah in September 2023 and kept its fuel. Rather than decommission it, NASA redirected it. OSIRIS-APEX, the Apophis Explorer, is en route. It will match velocities with Apophis before the flyby and watch the tidal distortion as it happens. It will record every surface shift, every settled boulder, every adjusted slope in real time. After the flyby, it will descend and fire thrusters briefly, disturbing the surface to study it. Is Apophis a solid, coherent rock, or a rubble pile held together only by weak self-gravity? The answer determines how to deflect an object of this type, if deflection ever becomes necessary. Rubble piles absorb kinetic impactors differently. A spacecraft might bury itself rather than push. One flyby, one set of observations from April 2029 will reshape asteroid science for a generation. Graduate students, not yet born, will cite data from those hours in dissertations across the 2040s. Consider what the full arc of this story demonstrates about the species that lived through it. 66 million years ago, a 10-kilometer impactor struck the Yucatan with no warning at all. No countdown, no probability, no press conference, no radar, no mitigation, just the event. The dinosaurs did not fail to track Chicxulub. They lacked the capacity to track anything. We are the first species in Earth's entire history to possess that capacity. We used it. We found a 340-meter rock years before it could produce its highest threat probability window. We measured its orbit across 17 years with 3 different generations of instruments. We calculated a thermal drift of 170 meters per year on a rock 250 million kilometers distant. We closed every threat window before any could become the thing that ends a century of history. This is not a story about a near miss. Apophis was never going to hit us, given what we now know. It is a story about what becomes possible when the instruments exist before the threat materializes. When the survey runs before the name appears. When the radar facility is staffed before the call. The serpent did not destroy the sun this time. Not because fate intervened, because arithmetic did. Thank you for staying with us until the very end of this journey through deep time. If this exploration moved you, subscribe and stay for the next ancient chapter. Your curiosity is what keeps these lost worlds alive.